The world is an amazing place, but how did we get to where we are? Well, to answer that question, there's a whole branch of sciences called origin sciences. And this tells us why the world came to be the way it is today. And it talks about everything from dinosaurs to the formation of black holes. Origin sciences is a vast and expansive set of topics that cover almost everything in our universe. But it all starts with a Big Bang. A huge explosion of both energy and mass that creates the entire universe as we know it. This is the starting point for all of origin sciences. But now that the universe is created, where do we go from here? Well, the first thing that we've noticed is that after the Big Bang, the universe has been constantly expanding. But how do we actually know it's expanding? It's because of this thing called the Doppler effect. It says that when an object moves further away from us, the light it produces looks lower in frequency, or more red. It's a process we call redshifting. How do we know that this is happening to the universe? Well, when we look into the night sky, we see most of the galaxies actually fall in the infrared spectrum of light. Since the universe is expanding, you might expect everything to be super far away from everything else, but this doesn't happen. Why? Because of a little thing called gravity. It brings together a nearby collection of rock, gas, and dust to form a star and surrounding it many planets, a system of celestial objects that we come to know as our very own solar system, with many others like it scattering the cosmos. That's the incredible birth of our solar system. But what about its death? For our sun, eventually, in 4 billion years, it will run out of fuel and start to become massive, a red giant. It'll swallow up the rocky planets and make Earth uninhabitable. And like all stars, our sun will eventually run out of fuel. The way this happens is a little bit different depending on how much mass the stars have. For medium-sized stars like our sun, they turn into white dwarfs, their mass condensing into a small location. While they still have the same gravitational pull, they produce little to no light. Larger stars, however, will turn into neutron stars, which are extremely dense masses, about the size of New York City. These masses are extremely dense and extremely volatile, but they don't even compare to black holes. These massive wells of gravity are left behind by the collapsed masses of supermassive stars. They suck in everything, even light, and represent some of the most mysterious parts of our universe. But our universe has so much more than just the remains of stars. Our universe is riddled with exoplanets, or planets that exist outside of our solar system. And generally they're hard to find, but recently science has gotten better at not just finding them, but finding if they could even be suitable for life, which is an amazing scientific discovery. And there are a few really cool ways that scientists are finding these new exoplanets in our universe. One of the first methods is astrometry, and here scientists utilize the fact that gravity works both ways. Not only does the star have a gravitational pull on its planets, but the planets also pull the stars. And this tiny pull creates a little bit of the wobble in the star's rotation. And by measuring this wobble, scientists are able to figure out what kind of planets must surround the star. Another way is direct imaging, where scientists cover up a bright star in an image, hopefully to reveal some dimmer objects surrounding it, often exoplanets. Another method is called gravitational lensing. Here you can see how light can actually be bent by gravity. So then when a planet travels along with a star, we can measure the bending of light and use that to detect which stars should have exoplanets surrounding them. And there's another method that also uses the wobble of stars, but slightly differently. Here we can see that the star emits light, but due to its wobble and the Doppler effect, the light it emits is slightly different based on where it is in the wobble relative to us. And by measuring the light that comes out and by noticing fluctuations in the wavelength, we can figure out if a star is wobbling and by how much, which can give us valuable insight onto where its exoplanets might be. There's another method called the transit method, and what this says is that as a planet starts to cross in front of the path of a star, the amount of light we get from that star decreases. And by noticing this decrease in a star's light, we're able to gather info about exoplanets that may surround it. And this strategy holds true not just for one star, but for multiple stars as well. And as we can see here, the light graph that's produced actually ends up being quite complicated. But by analyzing it, we can determine not just how many stars they are, but of what size they likely are. And this gives us a lot of information about the star and the planets that surround it. Now, we could spend an eternity talking about all the cool and awesome things we find in the universe, but let's shift focus back to Earth. This first period in Earth's history is called the Hadean Eon, and at this period in time, Earth is constantly being bombarded with celestial material and is extremely hot and volatile. It's actually during this period that the moon is formed. See, the Earth is approached by an object about the size of Mars, and after they collide, there's so much debris. A lot of it collects back and forms the Earth as we know it, but the remnants form what's now the moon. And it's an amazing process that you can see visualized here in this computer generation. And scientists are theorizing now that this process only took about a couple of hours to happen. And this just shows how dangerous and volatile the Hadean era was for Earth. There was no chance for life to survive during this tumultuous time period, and there was no stability in Earth at all. After millions of years, the Earth starts to cool down. We now have an atmosphere full of methane, carbon dioxide, and oxygen, and we have emerging plate tectonics that are going to all be very vital to life, making Earth more habitable. But how does life actually emerge? Well, there's two main schools of thought. The first one is called the primordial soup theory. This relies on the Miller-Urey experiment, which showed how with water, gases, and a little bit of energy, we could independently create amino acids, which are the building blocks of life. And it seems like we don't need any other theory for life. That is, until a meteorite landed in Murchison, Australia. This Murchison meteorite, when analyzed by scientists, revealed it had over 70 amino acids. And these amino acids weren't from Earth. They were from some other planet or celestial body outside of our solar system. And this was a massive revelation to scientists, as they realize now that amino acids could have come from space. So now, we don't know whether amino acids were actually from Earth, or if they came from some meteorite, or maybe a mix of the two. But either way, we know for sure that amino acids were the start of life. By having these amino acids, we were able to chain them together and to create proteins and RNA, which is self-replicating, which means that we can create life, essentially. So we know how to find life on Earth, but how do we use this same knowledge to find life on other planets? Well, it turns out we can just look at the atmospheres. On our planet, we have methane and oxygen in the same atmosphere. Most of the time, this doesn't happen because they like to interact with each other. But because we have life on Earth, we're able to keep on producing equal amounts of methane and oxygen and keeping a balance in our atmosphere. So if we simply look for planets or moons that have a balance of methane and oxygen, we can infer that they might have some sort of light that is restoring the balance. And using this method, scientists have been able to find many moons of Saturn that could potentially be hosts for life. Now, while these moons currently aren't suitable for life, either due to being extremely cold or having extremely rough terrain, they give a lot of promise that perhaps life isn't as hard to find as we previously thought. I mean, it's truly amazing the advances we're making in finding signs of life outside of our planet. But we also have to take a minute to realize how much we know about life on our own planet and the way it's evolved through time. I mean, how do we know so much about what happened millions or billions of years in the past? One method you're probably familiar with is called carbon dating, where we use different isotopes of carbon to try and figure out how old things are. But the problem with using carbon is that it has a half-life of 5,000 years. Now, while that sounds like a long time, that means that we can only really use it for about 60,000 years into the past. And since Earth's history runs over the course of many billions of years, it really isn't that effective in the grand scheme of things. So this is why scientists opt to use materials like uranium or potassium due to their higher half-lives. But in addition to radioactive decay, scientists can also use Earth's changing magnetic field in order to get more precise measurements. How? Well, depending on which way the magnetic field is flipped, the rocks in a rock layer will either be facing in one direction or a different direction due to magnets. And what this means is that within a rock layer, by analyzing which way the rocks are facing, a scientist can get much more accurate age predictions, which help him tell the age of fossils in the surrounding rock. And all of this can help us understand amazing phenomenon like the rise of the dinosaurs and then the eventual extinction of the dinosaurs. Now, that video really covered a lot of topics in a very short amount of time, but regardless of what interested you, it's all origin sciences, and it's all part of putting together the puzzle of our existence. And it doesn't matter which field you get into, but these are important questions, and they pose existential problems that really have such impact on life and meaning. Maybe we'll derive some meaning from our findings, but maybe we won't. Regardless, we're gonna find a clearer picture of our history and perhaps even our future. This field of science has so much left to offer, despite all that we already know. And hopefully this inspires you to look into it and dig deeper into the many topics that are coming to the surface. Thanks for watching, and I hope you have a good day.